Hi guys, so in this video I'm going to be going over Lewis structures as well as explaining formal charges and how to find the most appropriate Lewis structure. So first we need to know how to draw a Lewis structure. So first step is counting the total number of valence electrons, which is group number and multiplied by subscript. What this means is, say you have CO2 for example. C has 4 valence electrons because it's group number 4. O has 6 valence electrons because it's group number 6, but since there are 2 O's, the subscript is 2, you multiply by 2, so the total number of valence electrons here is going to be 16. So, then you choose the central atom, which is usually the least electronegative atom. Again, taking CO2 as an example, this would be the central atom. It's rarely halogens and oxygen, and it's never hydrogen, because hydrogen only has 1 electron and can form 1 bond. So, draw the atoms with a single bond between the central atom and each outer atom. So we'll start with O, C, O, just like this. Each single bond is 2 electrons. Use the rest of the electrons to fill the octet, put 6 around each outer atom. So we have 2, 4, so that means we have 12 electrons left over. So let's start putting electrons on the O's. 6 on this O and 6 on this O. We're left over with 0 electrons. So if there are any leftover electrons, put them as lone pairs on the central atom. We don't have any, so we're going to skip to step 6. Check the central atom. Central atoms should have 8 electrons around them. This is known as the octet rule. But there are actually a few exceptions to the octet rule. Beryllium, Be, usually has 4 electrons around it. Aluminum and boron usually have 6 electrons around them, so compounds with aluminum and boron are usually called electron deficient. If an element is below period 2, it can have more than 8 electrons around it. That's because elements below period 2 also have d orbitals, but elements in period 2 only have p orbitals. But an element in period 2 must have 8 electrons around it, so this applies to carbon. If after completing all the steps above it doesn't, then you start removing lone pairs on outer atoms and using multiple bonds. So right now, carbon only has 4 electrons around it. We need to bump that up to 8. So what we can do is get rid of 1 lone pair on one of the oxygens and make this a double bond. Now it's 6 electrons around it. Still not good enough, so we need to take another lone pair off the other oxygen and make it a double bond. Now oxygen has 8 around it because 2, 4, 6, 8, and the other oxygen has the same, and carbon has 8 around it. This is the proper Lewis structure. And one more, when more than one Lewis structure is possible, we can say the compound has resonance structures. What this means is that it doesn't take just one structure, it occupies all 3 structures and it kind of cycles through them. For example, let's take SO2. So SO2, both S and O are in group 6, so 18 valence electrons. We'll draw the S with the O's, fill the octet. So there are 6 on each oxygen and each double bond is 2, so 2, 4, 6, 8, 10, 12, 14, 16, 2 electrons left over, so we're going to put them on the central atom, and we count 2, 4, 6. This is not proper, so we need to get rid of a lone pair on one of the oxygens and make it a double bond. Now S has 8 electrons around it, everybody's happy. But you can also do the same thing on the other oxygen, take away a lone pair, and make it a double bond. So that basically means that SO2 has 2 appropriate Lewis structures. One where the double bond is on the first O, and one where the double bond is on the second O. But scientists, when they tried to measure the bond length of SO2, they thought, well, okay, looking at the structure like this, you would assume that one bond is going to be shorter than the other. But actually, no, both bonds are the same length between the length of a single bond and a double bond. So longer than a double bond, but shorter than a single bond. So that's why we have resonance structures. Okay, after that is over with, now we're going to know how to find formal charge on an atom. So to find formal charge of an atom in a compound, you use this formula, which is the number of valence electrons in the free atom, aka group number, minus the number of lone electrons plus the number of bonds leaving the atom, so half the bonding electrons. So the best Lewis structure for a compound is the one where the formal charges are all equal to 0, but that's not always possible. So the best Lewis structure is the one that has as many zeros as possible, and make sure that the most electronegative atom should have the lowest formal charge. So an example of this, we're given two structures of HCNO, structure 1 and structure 2. We want to use formal charges to predict the most appropriate structure. So in both structure 1 and structure 2, the FC of H is going to be 0 because it's 1 minus 1, so 0. So we can ignore H for this example. For the first one, the formal charge of C is 4, which is the group number, minus 0, because there are 0 lone electrons, plus 1, 2, 3, 4. So it's 4 minus 4, which is 0 here. For nitrogen, it's 5 minus 4, which is plus 1. Make sure whenever you solve any question on formal charges, if the charge is positive, put a plus. If the charge is negative, put a minus. Otherwise, you will get the question wrong. And for O, it's 6 minus 6 lone electrons plus 1 bonding, so 6 minus 7, so minus 1. That's structure 1. Now we're going to take a look at structure 2. The formal charge of hydrogen is the same as structure 1. The formal charge of carbon is going to be 4 minus 1, 2, 3, 4, 5, which is minus 1. The formal charge of nitrogen is going to be 5 minus 4, which is plus 1 again. The formal charge of O is going to be 6 minus 1, 2, 3, 4, 5, 6, which is 0. So we'll take a look at them, and we're going to compare structure 1 and structure 2. Both of them have the same number of zeros, but if you look at structure 2, O is the most electronegative atom, so it should have the lowest formal charge. But in structure 2, the formal charge of carbon is minus 1 and the formal charge of oxygen is 0, which is wrong because oxygen should have the lowest formal charge. So we choose structure 1. Structure 1 is the most appropriate structure. We'll take another example. Another example, you have the phosphate PO4 minus ion. Use formal charges to find the most appropriate structure. So we'll look at this one first. Just for convenience, we're going to call these O's O1, O2, O3, and O4. So the formal charge of P here is going to be 5, which is the group number, minus 4, so plus 1. And the rest of the O's are going to be 6, minus 7, so minus 1, minus 1, minus 1, minus 1. If you take a look at structure 2, we took a lone pair off of O1 and we made a double bond there. So the formal charge of P is actually going to be 5 minus 5 now, which is 0. And the formal charge of O1 is also going to be 0 because it's 6 minus 6. And the rest of the O's, O2, O3, O4, are going to have the same formal charge, which is minus 1. Take a look at structure 3. We took off a lone pair on oxygen 2, and we made another double bond. So the formal charge of P is going to become negative, which is wrong. O1 and O2 are going to have zeros, and O3 and O4 are going to have minus 1. Structure 2 and structure 3 have the same number of zeros, but the problem with structure 3 is that P has a negative formal charge, but O is the most electronegative atom, so it should have the lowest formal charge. And that's why we choose structure 2. This is also another example of resonance structures. In one structure, the double bond is going to be here on O1. In another structure, the double bond is going to be on O2. In another one, it's going to be on O3. And another one, it's going to be on O4. And the compound rotates through those 4 resonance structures. So structure 2 here is the most appropriate structure. Thank you.